In this video, I'd like to talk about the average rate of change of polynomials. And before we start looking at specific problems, we want to think about what is the rate of change and how do we take an average of that? So you might recall learning about the concept of slope when dealing with linear equations. For instance, if we have y equals 2x minus 1, and we were to get some type of graph of this, we can plot the y-intercept. I'm using the slope-intercept form here, where b is our y-intercept, so it goes through at minus 1. And m, the number multiplied by x, this coefficient here, this is the slope. And in our case, it's 2, or 2 over 1. And so essentially what that means is that every time we go over 1 in x, we go up 2 in the y direction. So we can draw the line now. And with these linear equations, what we call the slope of this line, the steepness of the line, this is the rate of change. It tells us that for every x value we go over 1, we go up 2 units. And it tells us how much the y values are changing. This symbol here, this is the Greek letter delta. It means change in. So it's the change in the y values divided by the change in the x values. And you can see the y values change by 2 every time the x values change by 1. And for a linear equation, we say this has constant rate of change. Since this slope, this rate of change here, is itself never changing. It's always going to have this steepness where every time you go over 1, you go up 2 units. This stays the same, or it stays constant throughout the entire graph of this entire line. So the average rate of change for polynomials is essentially we're going to take this idea, this rate of change, this slope here for lines, and extend it to curvy functions. And it doesn't have to just be for polynomials. That's what we'll cover in this video. But it could be for really any class of function, since the idea of rate of change is incredibly important. You can imagine all the different things in nature or human interactions where things are changing. And understanding how quickly those things change is very useful. Speed is an example of a rate of change. When you're driving down the highway, let's say 60 miles an hour or maybe 100 kilometers an hour, depending where you're at, then that describes your rate of change, how many miles or kilometers you're going per hour. And that might even change. You might hit the accelerator or hit the brakes, and your rate of change itself would change. And understanding that process of how quickly something is changing, that can be useful for so many different applications. So let's now extend this idea to polynomials. So if I were to graph this, now you might remember from the shifting and reflecting of polynomials. So let me just rewrite it. G of t is minus t minus 1 squared plus 5. So the negative gives us a reflection, and the rest of this is in vertex form. You could think we shift it right 1 because that's the t value that would make this expression 0. And then we're adding 5 on the outside, so that shifts everything up 5. So it goes through the point 1, comma 5 here, right here, and it's reflected downward. Now you could also plot some points. If you plug in 0, you should get a y value of 4. If you plug in 2, you'll get a y value of 4, and so on. This function will look something like this. It's just a downward facing parabola. And we could get more exact. You can plug this into your graphing calculator or into Desmos to get a better picture. But what we want to do now is look at the average rate of change of this polynomial over this interval. So let me write down the interval, since that will be important. So we're considering from a t value of minus 4 to a t value of 5. So maybe somewhere around here to somewhere around here. And we want to know how, on average, is this function changing? And again, this is only going to give us an average, an approximation of how it's changing. because if you want to know exactly how it's changing, that's where calculus comes in. And I'll get to that in a moment. But for this exercise, and really for all of these exercises, what we're going to do is look at these endpoints on our interval. So this is when t is -4, and over here is when t is equal to 5. Notice the endpoints of the interval are included. And what we want to do next is figure out the y values at those points. So at least for this one, we can get a picture of what's going on, but in general, you need the y value so that you can use the formula to find the rate of change between these. So let's plug these into the function. We have g of -4. So you get -4 minus 1, which is -5, squared, which is 25, and then we take the opposite. So -25 plus 5, that would be at -20. When we plug in 5 to our function, you get 5 minus 1, which is 4, squared, which is 16, and we take the opposite. So -16 plus 5, that would be at -11. And it looks like our graph here is not going to go far enough down, so let me just kind of extend this, and we'll have to imagine this a little bit. So let's say at -4, that is maybe this point right here. We'll call this -20. And at 5, let's say maybe, actually let me draw in the markers, 2, 3, 4, and then over here, let's say 3, 4, 5. And this is not to scale, but this is just to give us a rough idea of what's going on. So at 5, we were at -11. So maybe it's somewhere over here. Again, I didn't draw this too perfectly. And let's call this -11. So we're able to plot these points on our curve. That's the key idea here, is that we're just looking at the endpoints for this interval, and we want to plot those x and y values somewhere on our graph. In reality, when solving these, like I said, you don't need to plot these, but if you want to understand what's going on, having a visual really helps. And once we've plotted these points, all we're going to do is essentially just draw a line between them. So let me use my line tool, and we will connect these with a straight line. And the average rate of change is just asking, what is the slope of this line? Since if we know the slope of this line, we can roughly approximate how the function changes between these 2 points. And again, it is a rough approximation, especially since these 2 points are so far apart. But let's calculate that so that we can interpret it. So remember, when you're finding slope, and I'll use the letter m again, and again, this is just the rate of change. This formula is just the change in the y values divided by the change in the x values. Or you could even think it's the change in the function values divided by the change in the x values. And we can often look at different formulas, but they'll mean the same thing. So usually, change in y, you have your second y value minus your first one, divided by your second x value minus your first one. You might remember this formula from your Algebra 1 class. Now, we could also write it in function notation, because y2 is the same thing as g of x2, where you just plug in your x2 value into the function, and that will tell you your y value. These are equivalent to each other. So you'd have g of x2, and then we'd subtract g of x1, since that's really just y1. We plug in x1 to our function, and we get the y value associated with it. And then down below, you would still have x2 minus x1. So to find the slope of this line, we're just going to plug in our points. So we know that, let's say t of 5, let's call that x2. So when we plugged in 5, we can call that y2. Or really, this is just g of x2. And so we have -11. Let me use a different color here. -11 for our y value. And then if we call this x2 and y2, that makes this x1, and this would be y1. So we have minus y1, and we're subtracting a negative, so be careful here. I would recommend putting it in parentheses so that you can recognize that you are subtracting this negative and change it to addition, since you're doing the opposite of subtracting. And in the bottom, you have x2, which is 5, minus x1, which is -4. Again, we'll put it in parentheses. So here you have -11 plus 20, divided by 5 plus 4. So that's 9 divided by 9, which is 1. And so what we found is a slope of 1, or you can write it as 1 over 1. So every time that x changes by 1, the y value also changes by 1. But again, this is an average between these 2 points. On average, every time x goes up by 1, the y value also goes up by 1. But you can see that this is a very rough approximation, because in the beginning, as x goes up by 1, y goes up by a lot more than 1. And it starts to slow down as you approach the vertex, and then around the vertex, it essentially flattens out and changes and goes in the other direction. Now, every time x goes over by 1, y actually decreases. And so this slope doesn't really tell the whole story. It kind of roughly tells you that from this point to this point, you're going to go up in value. Every time you go over 1, you go up 1. But it doesn't tell us much about what's happening between those 2 points. In fact, once you're at this point over here, it's going very steeply downward. And I mentioned that this relates to calculus. This is actually the foundation of calculus, or the first part of calculus, which is differential calculus, or involving something called the derivative. And in calculus, what we do is, instead of looking at 2 different points that are far apart, what we really do is start with 2 points that are close together and essentially make 1 point move until it's pretty much on top of the other point. And in that process, we no longer have an average rate of change. Now we will have an exact rate of change. And what that looks like graphically is you end up getting a tangent line. So you get this line that is tangent to the graph, meaning it's just touching it at that one key point, and the slope of that tangent line would be the exact rate of change. So you can see down here it's very steep, this tangent line. But as we go up, let me use a different color that's more vibrant. As we go up, that tangent line is going to get less and less steep because the function is leveling out. And as we reach its peak, the tangent line actually becomes flat. And at that point, the function isn't changing. And it's the slope of that tangent line would be 0, and then you keep going down. And now that tangent line is getting very negative, because on this part of the curve, as you increase the x value, the y value goes down. And as you keep going and going, that tangent line just gets more and more steep because our curve itself is getting steeper. So this rate of change, when you have a curvy function, is itself constantly changing. That rate of change is not constant like we had with a linear equation. The rate of change is either accelerating or decelerating. So, like I mentioned, in calculus, you will look at this exact rate of change, where you essentially just plug in 1 point to what's called the derivative, and it tells you the slope of this tangent line. It tells you exactly how much the curve is changing at that given point. But for our practical purposes, what we're doing is we're always going to be given 2 values, which we could plug into the function and get the y values for those points. We can plot those points, and the average rate of change is just finding the slope between these 2 points. And you don't have to plot this out every time. This is just to help you understand what's going on. You want to plot the points if you really want to see the picture and draw this line and visualize what that average change means. And in our case, we found an average rate of change of 1. And so that means, on average, every time we go over 1, we go up 1. So when we go up to our question, the average rate of change over this interval is simply equal to 1.